We discussed the position space wave function. Now let's move on to the momentum space wave function. So far we have worked exclusively in the x basis. Okay, that is, we used a basis formed by the eigenkets of the position operator. We called this the position representation or coordinate representation. Now there is actually a complete symmetry between x and p. You might be familiar with this from your classical mechanics. In the Hamiltonian formalism, you might have treated x and p symmetrically, right? But there could be an occasional minus sign. Okay, there will be an occasional minus sign, right? For example, if you look at the commutator of x and p, this is I h bar. But if you interchange x and p, all right, instead of x, if I write p, and instead of x, I write so instead of x, I write p, and instead of p, I write x, then I get a minus IH bar. All right. So relations involving positions and momentum have this symmetry actually. All right. For example, let's look at this relation. We had the commutator of xi with some function of the position operator. Okay. We said that this is equal to IH bar partial derivative of f with respect to pi. With respect to pi. Okay. All right. Now from this we could actually find the commutator pi with some function of, let me write as g, some function of x. All right. We'll see that this is equal to, here what I have done is wherever x appears here I have put a p, and wherever p appears here I have put an x. All right. So this would be also IH bar partial derivative of f with respect to x this time. All right. But there will be a minus sign. But there will be an extra minus sign. All right. So it's not completely symmetric. There is an occasional minus sign. All right. So this is a relation involving x and p. All right. Xi and a function of p vector. Right. Here we have replaced all x in this expression, in this entire expression. Every x has been replaced by the corresponding momentum, all right, and every momentum has been replaced by the corresponding position, right? And then the relation works, except that I have to put an extra minus sign, right? So there will be an occasional minus sign. Apart from that, everything is symmetric, all right? So just like in classical mechanics. So there we can see this thing clearly in the Poisson bracket formalism, right? So now let's move on to the p basis. So in this basis, this will be called the momentum representation. All right. So here what we'll do is that we'll use the eigenkets of the momentum operator as the basis. All right. We'll use the eigenkets of the momentum operator as the basis. All right. So the base eigenkets in p basis specify. So what are the base eigenkets? These are the momentum eigenkets. So they satisfy this relation. The momentum operator acting on ket p prime is equal to p prime multiplied by ket p prime. So this is the eigenvalue equation. All right. So in our notation, for operators we don't give prime. For eigenvalues we give a prime. All right. That's the notation that we have been following. Right. So this is the eigenvalue relation. So the eigenvalue equation. And we have got the set of all eigenkets of the momentum operator. And we know that, all right, we can assume that this forms a complete set, a complete orthonormal set. And the orthonormality relation is given in terms of the Dirac delta function. If I take bra p prime, ket p double prime, this is delta of p prime minus delta. So delta of p prime minus p double prime. Okay, so this is the orthonormality relation. This is how we write the orthonormality relation in the case of a continuous set of eigenvalues or a continuous spectrum of eigenvalues. All right, or in a continuous basis. Okay, so if it's a discrete basis, we use the Kronecker delta, and if it's a continuous basis, we use the Dirac delta. So as we said, the momentum eigenkets, the set of all eigenkets of the momentum operator, span the ket space in much the same way as the position eigenkets do. Right? We have seen this in the case of position eigenkets. The treatment is exactly the same. Right? Instead of using this set of vectors as the basis, I'm using this set of vectors as the basis. That's all. Okay. Now, an arbitrary state ket alpha can be expanded. All right. So what we do is that we have the completeness relation as usual. Right. Identity operator is equal to integral dp prime ket p prime bra p prime. Right. This is the completeness relation. Right. So we can just write ket alpha is 1 multiplied by ket alpha, or the identity operator multiplied by ket alpha, which is written like this. All right. Now it can be interpreted as follows. These are the expansion coefficients, all right, corresponding to the direction ket p prime. Right? So these are the base vectors, and corresponding to each base ket, right, corresponding to each base ket or corresponding to each base vector, you have an expansion coefficient. All right. So we can, as we did in the case of position basis, we can write this as a function of p prime. Right. We'll do that. Now, as usual, these expansion coefficients also have a probabilistic interpretation, just like we did in the case of position. All right, so we'll just state it here. The probability that a measurement of P, measurement of momentum, gives an eigenvalue P prime within a narrow interval dP prime. All right, so we are asking the question, what's the probability that the momentum is between P prime and P prime plus dP prime? All right, so if you make a measurement of momentum, you can ask what's the probability that it's within an interval dP prime around P prime. All right, you can write it like this. What's the probability that the momentum is between P prime and P prime plus dP prime? All right, this is written as bra P prime ket alpha modulus squared multiplied by dP prime. All right, so this again can be thought of as the probability density in a way. All right, the probability density in momentum space. This would be the probability. All right, I think we have explained this sufficiently in the case of the position basis. The concept is the same. All right, so we shall not go into so many details again. All right, I think the idea is clear. All right, so these expansion coefficients have the probability interpretation just like these expansion coefficients have the probability interpretation. Okay. It's customary to call bra p prime ket alpha the momentum space wave function. It's called the momentum space wave function. And the notation we use is phi alpha of p prime. Right? For the case of position space wave function, this is the notation we used. Bra x prime ket alpha is psi alpha of x prime. For the momentum wave functions or the momentum space wave functions, we use phi alpha of p prime. Right? So bra p prime ket alpha is written as phi alpha of p prime. This means that corresponding to every p prime, this function returns a complex number. This complex number will allow us to calculate the probability for measuring the momentum in a specific small interval. All right. Now the normalization condition, if ket alpha is normalized, we can write this as, this means that bra alpha ket alpha is equal to 1. Well, this is the normalization condition. Okay. Now introducing an identity operator in here, all right, in terms of the completeness relation of the momentum eigenkets, we can write this as bra alpha integral dP prime ket p prime bra p prime ket alpha is equal to 1. This is the identity operator. Or integral dP prime bra alpha ket p prime bra p prime ket alpha is equal to 1. All right. Now what is this? This bra p prime ket alpha is what we called phi alpha of p prime, right? And what is this? This is just the complex conjugate of this. So this can be written as phi alpha star of p prime. So normalization condition becomes integral dP prime phi alpha star of p prime, which means the complex conjugate, right? Phi alpha star of p prime multiplied by phi alpha of p prime. Okay. Now that can be written as modulus square of phi alpha of p prime. This is written as modulus square of phi alpha of p prime. All right. So normalization condition is integral dP prime modulus square of phi alpha of p prime is equal to 1. All right. So this is very similar. It's exactly the same thing that we have seen in the case of the position space. All right. So we have now two representations, the x representation and the p representation. Right? So we should be able to go from one basis to another, right? One basis to the other. Right? So let's now establish the connection between the x representation and the p representation. Okay. Now in the case of discrete spectra, we saw that the change of basis from an old set ket A prime to the new set is characterized by the transformation matrix bra ak u ket al is equal to bra ak ket bl. All right. So here u was the unitary operator that takes us from the old set to the new set. All right. So if I have a ket from the old set, I can apply this unitary operator to it, and I'll get a ket in the new set. All right, and we looked at the matrix elements of this unitary operator in the old basis, and this is how the matrix elements are. All right, these are bra ak ket bl, and these obviously depend on the old set as well as the new set. Right? We are talking about a transformation from the old set to the new set, and obviously this matrix elements depends on the old set as well as the new set. All right. Now, in the same way, we expect that the desired information is contained in bra x prime ket p prime. Right. Now we are talking about going from the position basis to the momentum basis. All right. So the information should be contained in bra x prime ket p prime, just like this. All right. Here this was a matrix. In this case, this would be a function. All right. So these were the elements of a matrix, to be precise, and here we have a function. Right? It's a function of both x prime and p prime, and we'll call this the transformation function from the x representation to the p representation. All right. Now there's another way to look at it. If I take a momentum eigenket, I can expand it in terms of the position eigenkets. So I can write this as integral dx prime bra x prime, sorry, ket x prime bra x prime ket p prime. All right. So what I have done here is that I have taken this momentum eigenket and I have expanded it in the position basis. These are the basis vectors and these are the expansion coefficients. All right. And you might identify already that this is the completeness relation for the position eigenkets. All right. Okay. So clearly we see that the necessary information from going from this basis to this basis is included in this or in this function. All right, it's included in this function of both x prime and p prime. All right. Now we need to derive the explicit form of bra x prime ket p prime. Right. For this we recall bra x prime p ket alpha is equal to minus ih bar partial derivative with respect to x prime of bra x prime ket alpha. All right. So the idea is that ket alpha is represented in the position basis by the function bra x prime ket alpha. Right. The question is, what's the representation of p ket alpha in the position basis? All right. So this relation says that the representation of p ket alpha in the position basis is obtained by applying minus ih bar partial derivative with respect to x prime on this function. Okay. Now what happens if instead of ket alpha we have the momentum eigenket ket p prime? All right. So then we can write bra x prime p, instead of ket alpha I have a ket p prime here. Right. Obviously this equation says that this is equal to minus ih bar partial derivative with respect to x prime of bra x prime ket p prime. Okay. Now this ket p prime is an eigenket of operator p and it satisfies the eigenvalue equation. P acting on ket p prime is p prime multiplied by ket p prime. Right. So this now is a number. This p acting on ket p prime can be written as the eigenvalue p prime multiplied by ket p prime. All right. Now this is a number, I can pull it outside. So this becomes p prime bra x prime ket p prime is equal to minus ih bar partial derivative with respect to x prime of bra x prime ket p prime. All right. Now this is the function that we needed. This is the function. This was the transformation function that we were talking about. All right. We have got a differential equation satisfied by the transformation function. All right. Here what we have is a differential equation satisfied by the transformation function. We just have to solve this to get the transformation function. Okay. Now this is the differential equation that needs to be solved. We can rewrite it as follows. We can write this as partial derivative with respect to x prime of bra x prime ket p prime is equal to I p prime divided by h bar bra x prime ket p prime. Right? Now the solution has to be obvious because we are talking about a function. We are talking about a function of x prime and p prime, which when you take the partial derivative with respect to x prime gives you the same function multiplied by a factor I p prime divided by h bar. Right? So when I'm taking partial derivative with respect to x prime, p prime is held a constant. All right. So we know a function like this. All right. When you take the derivative, you get the same function multiplied by something else. All right. So this function is the exp function, the exponential function, which is written as. So we know that it has to be of this form, right? Exponential of x prime. So this will give me, if I take the derivative with respect to x prime, this will give me the same function, right? But I need the same function multiplied by this factor, which means that this factor has to be appearing here. All right. So the solution is exponential I p prime x prime divided by h bar. Right. There is also a normalization constant which has to be determined. All right. Now this is the transformation function, which is a function of two variables x prime and p prime. All right. Now let's look at it in a slightly different way. Let's fix this p prime. All right. Let's fix this p prime. Then what does this equation tell us? Right. If we fix the p prime, this means that we are talking about ket p prime projected onto the position basis. Ket p prime projected onto the position basis. In other words, we are talking about the representation of the momentum eigenket in the position basis. Right? This is the representation of the momentum eigenket in the position basis. All right. And for this reason, we know that this is how we write the normal wave function. All right. If you have a ket alpha, the corresponding wave function is bra x prime ket alpha. All right. So instead of ket alpha, I have the momentum eigenket, and the corresponding wave function is bra x prime ket p prime. All right. Now this is called a momentum eigenfunction. This is called a momentum eigenfunction. Okay. So it is just the wave function for the momentum eigenstate ket p prime, and it's often referred to as the momentum eigenfunction. All right. And what does this bra x prime ket p prime give us? All right. It is the probability amplitude for the momentum eigenstate specified by ket p prime to be found at position x prime. Right. So we are talking about a system which is in a momentum eigenstate. All right. The system is in a momentum eigenstate. The state of the system is a definite momentum state. Right. It has a definite momentum. Okay. Now we are asking this question: if you are given a momentum eigenstate ket p prime, and I am trying to measure the position on this state, I am trying to measure the position on this state. All right. What's the probability amplitude that this state is found around x prime? All right, or at x prime. What's the probability amplitude that this system is found at x prime? We know the rule to find this probability amplitude. It's you just have to project this ket p prime onto the corresponding eigenket of the position operator. All right. So you can view this as the probability amplitude for the momentum eigenstate. So this thing is the probability amplitude for the momentum eigenstate specified by the eigenvalue p prime to be found at a position x prime. All right. So what are we talking about? We are talking about the x space representation of the momentum eigenket. This is the x space or the coordinate space representation of the momentum eigenket, and it's called as a momentum eigenfunction. Okay. So this solution simply says that the wave function of a momentum eigenstate is a plane wave. Okay. Now this is called a plane wave. It is amusing that we have obtained this plane wave solution without solving the Schrodinger equation. Now we have not yet seen the Schrodinger equation. Later we'll see that the wave function of a physical system evolves according to the Schrodinger equation. In time it changes according to the Schrodinger equation, or the time evolution of the wave function is governed by the Schrodinger equation. Okay. Now if you solve the Schrodinger equation for the free particle, for the case of a free particle, okay, we'll see that the wave functions are exactly the plane waves. Okay. So right now what we have here as the momentum eigenfunctions are also the free particle solutions for the Schrodinger equation. Okay. These are also the free particle solutions for the Schrodinger equation. Okay. The next task is to find the normalization constant. All right. Let's do it on the next slide. So we start with the orthogonality relation for position eigenkets. This orthogonality relation is written as bra x prime ket x double prime is equal to delta of x prime minus x double prime. Okay. Now, as usual, we introduce an identity operator in here in terms of the completeness relation for the momentum eigenkets. Okay, this is the identity operator that we are inserting here. So this equation becomes integral dp prime bra x prime ket p prime and bra p prime ket x double prime. Okay, now this has to be equal to delta x prime minus x double prime, the right hand side. All right, now this bra x prime ket p prime we already have written down. This was our momentum eigenfunction, which we wrote as n exponential I p prime x prime divided by h bar. All right, and this means that bra p prime ket x double prime is equal to, so we see that these are related by a complex conjugation, right? So bra p prime ket x double prime is equal to n star exponential minus ip prime x prime divided by h bar. Okay, actually it's p prime x double prime divided by h bar. All right, now if I substitute these two things back into this equation, there will be an n multiplied by n star, which is modulus n square. Right, so this equation then becomes modulus n square integral dp prime. What are we left with? We have got two exponential here. Right, so when we multiply these exponentials, we know that their arguments will get added. All right, so adding these arguments, we have exponential. This ip prime divided by h bar is common to both the arguments, so that can be pulled out. So this is ip prime divided by h bar. Then we have got x prime minus x double prime. Okay, now this is equal to delta x prime minus x double prime. Okay, right. Now you might have studied the integral representations of a Dirac delta function. Right, we see that this looks like the integral representation of the Dirac delta function, except for some problems here, right? So we can make a substitution. We'll write p prime is equal to, or p prime divided by h bar, we can write as a new variable k. All right, this means that dp prime will be written as h bar dk. So if I make this substitution, the relation becomes modulus n square, this h bar, all right? dp prime is substituted with h bar dk. So this becomes modulus n square h bar integral. Okay, here I have dk and exponential k multiplied by x prime minus x double prime. All right, k multiplied by x prime minus x double prime, because p prime divided by h bar is k, which means that I'll have an I here. All right, so it's ik x prime minus x double prime. Okay, now this is equal to delta x prime minus x double prime. Okay, now if you remember from your mathematical physics, Dirac delta function had this particular integral representation. We can write delta x prime minus x double prime as integral dk divided by 2 pi exponential ik x prime minus x double prime. All right, so this is an integral representation of the Dirac delta function. Now if you don't remember it from mathematical physics, it's all right, you can just memorize it now. All right, this is an important integral representation for Dirac delta function. Okay, so integral dk divided by 2 pi exponential ik x prime minus x double prime is delta x prime minus x double prime, right? Which means that on the left hand side I now have modulus n square h bar, right? Except for this 2 pi, this is the delta of x prime minus x double prime. So this is multiplied by 2 pi delta x prime minus x double prime, right? So this thing is 2 pi x prime minus x double prime. So this is 2 pi delta x prime minus x double prime, right? So this is equal to delta x prime minus x double prime, which means that modulus n square now has to be equal to, or modulus n square h bar 2 pi now has to be equal to 1. Okay, this means that modulus n square is equal to 1 divided by 2 pi h bar. All right, or we can write n is equal to 1 by square root of 2 pi h bar. Okay, can write n is equal to 1 divided by square root of 2 pi h bar. Right, so here we have chosen n to be purely real and positive by convention. Right, there could be an extra phase factor here, but that can be set equal to 1. Right, so we can make that choice without changing any physics at all. Right, so this phase factor is not important, we can choose it to be 1. So we can write n from here. We see that, let me write it here now, n is equal to 1 divided by square root of 2 pi h bar. Okay, which means that now this momentum eigenfunction can be written as 1 by square root of 2 pi h bar exponential ip prime x prime divided by h bar. Okay, so this is also a transformation function that we are looking for. Now let's see how the position space wave function is related to the momentum space wave function. We start with the position space wave function of ket alpha. All right, and then what we need is the relation between the position space wave function and the momentum space wave function. So in order to have a momentum space wave function, we can again introduce an identity operator in between here in terms of the momentum eigenkets, right? So this bra x prime ket alpha, or the position space wave function, this is psi alpha of x prime, right? Bra x prime ket alpha is psi alpha of x prime. This is equal to integral dp prime. Okay, that comes from the identity operator, and we have got bra x prime ket p prime and bra p prime ket alpha, and bra x prime ket p prime we have already found. This is 1 divided by square root of 2 pi h bar. Okay, and we have got exponential I p prime x prime divided by h bar. Okay, and bra p prime ket alpha is the momentum space wave function of ket alpha. We can write this as phi alpha of p, phi alpha of p prime, right? So multiplied by phi alpha of p prime. Right, now we can rearrange this. We see that psi alpha of x prime is equal to 1 by square root of 2 pi h bar integral dp prime exponential I p prime x prime divided by h bar, and here we have phi alpha of p prime. Okay, you might immediately recognize this as the Fourier transform. Okay, so what we see here is that the position space wave function is related to the momentum space wave function by a Fourier transform. This is a Fourier transform, right? This is a Fourier transform. Right, I hope you are already familiar with Fourier transform. If not, it's fine. This kind of transformation is called a Fourier transform. Okay, and in the same way, we see that bra p prime ket alpha, right? So we need to relate now the momentum space wave function to the position space wave function. So we introduce an identity operator in here in terms of the position eigenkets. Okay, so this is written as integral dx prime bra p prime ket x prime bra x prime and then ket alpha. Okay, again this bra p prime ket x prime is the complex conjugate of this thing, right? So this becomes, what is this? This is phi alpha of p prime. So this equation becomes phi alpha of p prime is equal to, okay, this 1 by square root of 2 pi h bar follows, and here we have got dx prime, this is exponential minus ip prime x prime divided by h bar, and this bar x prime ket alpha is psi alpha of x prime. Okay, now that's what we have here. All right, this is the position space wave function. Of course, there's an h bar here. Right, we see that the position space wave function is a Fourier transform of the momentum space wave function, and here we have the momentum space wave function related to the position space wave function. All right, so we see that the position space wave function and the momentum space wave function are related through a Fourier transform. Okay, so it seems that the mathematics we have developed somehow knows Fourier's work on integral transforms. Okay, so we have got the Fourier transform from our mathematical formalism, right? We haven't postulated it or anything. We just got it from our mathematical formalism. Okay, so we have seen the momentum space wave function phi alpha of p prime is equal to bar p prime ket alpha. Okay, and we have seen the probability interpretation, right? This is the probability amplitude for measuring a momentum p prime in a state ket alpha. Okay, then we had the momentum eigenket in the position basis, right? The momentum eigenket in the position basis, we saw that this has the form 1 divided by square root of 2 pi h bar exponential I p prime x prime divided by h bar, right? This is the plane wave. So the momentum eigenkets in the position basis are plane waves. Okay, and we called this as the momentum eigenfunctions. We also saw that the position space wave function, which we wrote as psi alpha of x prime, and the momentum space wave function phi alpha of p prime, these are related by Fourier transform. Okay, these are the things that we discussed in this class. Okay, so with that I'll conclude this session. Thank you.